Hello and welcome to the Daily Space for today, July 18th. As often happens, I am your host for today, Dr. Pamela Gay. We have some amazing stories today, and I'm so glad that you are all here to hear them. Uh, I didn't even know where to start, so I decided let's just start with things getting destroyed because that's always a good place to start. Astronomers have long been watching what all is going on in the Taurus Regia constellation area, where we have a lot of high density stellar regions, we have a lot of young star systems, and in particular, they've been watching one star. RW Aurigae A. This is a star in a binary system that on a regular basis undergoes rapid dimming. Now, unfortunately, when I say on a regular basis, I don't mean on a periodic basis. This is not one of those things that happens like clockwork, the way we expect things to happen in astronomy. Instead, the faintening has been getting more common. It has been getting deeper. And we think, thanks to the Chandra X-ray Observatory, we finally understand what's going on. We have often, as astronomers, tried to explain the presence of hot Jupiters, giant planets snuggled right up next to their stars, as a migration process where, for various reasons, these planets interact with the disk of dust and gas around their parent star, and as they continue to eat their way in, well, they get closer and closer and closer while they get bigger and bigger and bigger. The question has been, though, how exactly does this migration stop? One of the explanations that's often used is the star itself blows an empty cavity around it, and with a lack of more stuff to eat, a lack of more stuff to interact with and use to drag itself inwards, planetary migration comes to an end. Well, with RW Aurigae, the migration may not have ended for a few of these planets. It appears that planets have drifted so close to this host star that they have been torn apart, and it is this debris cloud of dust and gas that is spiraling inwards that periodically dims the light coming in from the star. And this dimming is coincident with X-ray emissions that seem to indicate this star is happy to eat the material of what was once a planet. If the system is being interpreted correctly, this is the first known example of a star eating one of its worlds, a star eating one of its own. It turns out this rather cannibalistic kind of behavior is seen many different places. Now, I see folks that are pointing out that this is Tabby star. This is another name for this object. It is actually named after the discoverer, well, not so much the discoverer as one of the scientists on the team that initiated in-depth follow-up on this object. And the name Tabby Star comes out of a Kickstarter fund that was put together to raise funds to observe this star in greater detail. So it turns out Kickstarter is good for more than buying that travel jacket that doesn't quite do what you thought. It instead can allow you to fund science, which gives you more to think about. So moving on to our next story of the day, I am sad to say that we have had what is likely to be our last data release from the Planck mission. This little spacecraft has been out there diligently observing the microwave background across a variety of different wavelengths that allows us to, well, get images like these that show us how our universe began and allow us to check for things like, hey, is our universe small enough and old enough that we can start to see light that has traveled in two different directions and is now meeting us on two different sides of the sky? Well, while we haven't been able to find in this image evidence of that small universe, what we have instead found is evidence that our universe works exactly how our standard model of the Big Bang predicts it will work. There was no new physics in Planck. There were new things that we need to chase down, anomalies, places that are colder than expected, things that, well, are just a little different than expected, but on small scales that indicate individual things occurring in our universe, but don't force us to remodel our model for how our universe became what we see and experience today. Now, this isn't to say that Planck closed the book on astronomy when it comes to microwave astronomy and studying the cosmic microwave background. It just closed the book at this resolution. More data is always wanted, and one of the big and compelling reasons we have to keep understanding the universe in the microwave is as we study the Planck data, we find that it is consistent with all of our other data sets in explaining what is the acceleration of the universe within some error. What is the component of dark matter? What is the component of dark energy? And what is the geometry of our universe? Now, while it helped us answer these questions, there is one major discrepancy that we still have between the Planck data and data looking at our more current universe. And this is the data that says how our universe has continued to expand over time. This is our Hubble constant. This is the expansion rate of our universe. We know that our expansion rate is actually accelerating over time. This was discovered with two different research teams in 1998 looking at distant supernova and measuring the absolute distance from the amount of light we received from the supernova, and using this light to also measure the recession rate of these supernova that would tell us how fast is their place in space accelerating away from the planet Earth. Looking at Planck data and other data of the earliest moments in our universe, and looking at our nearby understanding from variable stars and supernova, we get two different values for this expansion rate. Two different values that don't overlap in their individual error bars. And this tells us that either something weird happened between now and then, or we're just missing one small thing, or maybe many small things, in just how our universe is expanding. So while we have our big picture model absolutely correct, confirmed in amazing detail by Planck, we still have more to study. And now many of us are going to sit here waiting ever so impatiently for that next great mission to explore the cosmic microwave background, to get ordered up and launched and, well, help us understand new anomalies in space. Now, coming back a little bit closer to home, we have a new set of adaptations added to the Very Large Telescope down in Chile. This particular suite of telescopes actually includes 4 8-meter mirrors that have the capability of working together and independently are capable of doing truly amazing things. These telescopes have high-speed detectors that allow them to measure fluctuations in the shape of a small circle of atoms in the upper atmosphere that get excited and illuminated by a laser beam that they shoot off. By measuring how non-circular that set of illuminated gases appears, they're able to flex their mirror rapidly to compensate for these distortions, to take what might have once been, well, a messy twinkling image that was affected by the Earth's atmosphere, and effectively get the kind of image you get from the Hubble Space Telescope. Only instead of using a 2.7 meter mirror, something the size of the front of a bus, they're using an 8 meter mirror. Now, how faint an object we can see is directly related to the size of the mirror. With Hubble, we have an area of less than 9 meters. With VLT, subtracting out the small center where light gets reflected back through, we have just under a 64 square meter mirror. That's a pretty significant difference, which means that VLT will now be able to see significantly fainter objects than Hubble for the same period of time observed, and will get similar resolutions. This opens up the possibilities for all kinds of high-resolution science, looking at distant galaxies and other objects that, well, we're tired of waiting for James Webb, and we know Hubble's life won't last forever. So this opens new possibilities. Now, unfortunately, the area we're able to discover is, or rather, the area we're able to observe is only the smallest piece of the sky. It is a 7.5 arc-second wide region on the sky, which means this image of Uranus isn't that, it's not really that cut out from the total field of view. They are using 0.025 arc-second per pixels in their CCD, which is something I never even imagined. This is a system that literally leaves me speechless. On the left, you see an image that was taken with the VLT system without using their new adaptive optics. This is this blue smeary mess. On the right is what happens when they turn on their adaptive optics. Now you can see a red blotch here, an orange blotch here. These two blobs correspond to these two red and orange stars visible in the corrected image all the way to the right. We can again see here are two of the bright stars. Here are those same two bright stars. We're seeing everything. I can't wait to see a comparison of what VLT is able to now do with the Hubble Deep Field and all of these other things that have been our gold standard for this is as good as the data gets. Well, we have a ground-based telescope, a telescope you can walk up and touch and plant new filters and new instruments on without having to launch into space. We have a ground-based telescope that now gets us this resolution. So Webb can get us areas of the electromagnetic spectrum, different colors than we can see here on Earth. It allows us to see parts of the infrared universe that our atmosphere blocks. This telescope, though, allows us other windows at the same resolution. And I am in awe of what is being accomplished. And eagerly await the flood of papers that are going to come in the coming years. So on this stunningly beautiful engineering accomplishment, I'm going to wind up today's brief news and say, wow, that's all I've got. Wow. And this has been The Daily Space for July 18th. I am today's host, Dr. Pamela Gay, and this show is brought to you by CosmoQuest. At CosmoQuest, we work to put science in your brain and invite you to come to our website, cosmoquest.org, and take your knowledge and help us explore our universe. We currently have projects that ask you to help us map out our moon, Mars, Mercury, Vesta, the asteroid, and even our own planet Earth. CosmoQuest is put together through a collaboration of multiple universities led through the Astronomical Society of the Pacific and including the Planetary Science Institute and Youngstown State University. Normally, after the show, we have an Astro 101 class, but today, well, the need to get some scientific publications worked on is coming out as a higher priority than the stream. I am so sorry. So come back Friday, and Dr. Matt will be back to bring you more science. Now, I'm here to take your questions, and I just want to add, we're sustained by you. Please give us a follow. They're free. Every subscription helps sustain us, and every bit really does matter. So go ahead, at me in the questions, and I'll do what I can to, well, answer you with science. So I'm going to switch my views so I can less awkwardly look over at the chat questions. So I see Fenrig is asking, could we use digital methods instead of real-time optics, assuming we could record millisecond snapshots? Sort of. This is actually the principle behind how we get images of the stars orbiting the black hole in the center of the Milky Way galaxy. Astronomer Andrea Getz is one of the leads in pioneering what's called drizzle photometry. This is where you take extraordinarily high-speed images, you centroid each object as it moves around the sky, and very carefully and quickly align your images so that you can get a final image that more or less subtracts out all the movement put in by the sky. Now, unfortunately, while this can correct for the fact that a star may appear to dance kind of all over Kingdom Come, you're losing some of the absolute data on exactly how each individual object is getting warped and how it's not just the center of the star that's moving, but it's the shape of the star that is changing. With adaptive optics, you can take longer period images, allowing you to see fainter objects more effectively. And it also lets you correct for the shapes of the objects. So you get, well, better spatial data than you can get with what Andrea does, which is perfect for tracking orbits of objects around the black hole, but not perfect when you're trying to measure the storms on Uranus. So I see more questions on this. Let me see what I can combine. Paranor is asking, would adaptive optics possibly exclude data of the light frequencies filtered out? And Larry is asking, does the optical interferometric observations of the VLT yield an image? Okay, so we have two very different questions that I can't combine, but I'll do what I can. So what they're doing with VLT is they are taking images in multiple colored through filters. Let me go back to showing you the image. Whoops. There we go. Let me go back to showing you the image I had up earlier. You can see that this is a color image. Now, this isn't taken with a color CCD. This is actually taken with astronomers using a variety of different filters, where each individual filter looks at the stars in a specific set of colors of photons, frequencies of photons. By limiting what different colors come through, we're able to, well, first of all, recreate scientifically accurate color images that let us measure the temperatures of the stars, which is cool in and of itself. It lets us put together these beautiful color images. But it also lets us say, hey, blue light coming through the atmosphere gets transmitted slightly different than red light, gets transmitted slightly different than green light. Our atmosphere, the reason when we look at things we see them twinkling not just in position but also in color, is our atmosphere does different things to different colors of light. So we take filtered images, we adapt each of them, taking into account the peculiarities of the colors being viewed, and work together to build this amazing image. Now, this kind of image is taken with a single mirror used at once. And the reason this is the case is the Very Large Telescope has the ability to network together all 4 telescopes, as well as some additional 1-meter mirrors to do what's called interferometric observations. This is where the light along each different path can be combined to essentially digitally synthesize the effects of using a individual mirror that is the edge-to-edge distance between the mirror's edges. So if I take two 1-meter mirrors and I move them 200 meters apart, the resolution, the detail they are capable of getting physically is that of a 200-meter mirror. Now, the problem is our atmosphere doesn't really support that so well in optical light. And with infrared, we can actually get to the point we can combine this light, we can put it together, but that resolution is only going to be along the distance of those two mirrors. If those meters are 1 meter across and 200 meters across, you're going to get the resolution of a 1-meter mirror in, well, every direction except for where you have that 200-meter separation. So this would lead to strangely smeared out images where you have individual diameters, where you have amazing resolution, but everything else is smeared out because of this weird constraint on it not actually being a spherical mirror, it being a bunch of different individual high resolution paths. We use this kind of data mostly for spectroscopy, where what we're worried about is resolving things along an axis. They do build images in different ways, for instance, where they're looking for star spots, but it's not going to be something like this. So we have limitations on what we can do with our interferometric images. Where you see the super high resolution images put together by globe spanning radio telescopes, what you're actually seeing is each of those dishes looks at 1 pixel in the image at a time. So instead of scanning a 1,000 pixel by 1,000 pixel resolution image, they're doing 1 high resolution pixel detection, 1 high resolution pixel. So it's a different process that allows us to build these super high resolution radio images while preventing us from building these super high resolution optical images. I hope that answered your question. It was a complex one that is hard to get at the truth of. Pulling my chat back up. Looking to see, scrolling back to see if there were any earlier questions I missed. So I'm not really seeing any additional questions. There we go, from Fenric. Going back to Planck. Now that we have a lot of data, is there any significant anomaly in the cosmic microwave background? I think that depends on your definition of significant. What someone desperately trying to get funding and additional telescope time will call significant, your everyday human won't call significant, and someone working in a completely different field of science may not call significant. So we do see minor irregularities. There's a cold spot that we're still struggling to understand. But by and large, no. The Planck cosmic microwave background map matches what our standard models said should be there. The only really disturbing thing is that we're not currently getting the same measurement of the expansion rate of the universe from nearby data and from the Planck data. And this is work Adam Rees and others are working very hard to figure out how to sort, and hopefully we'll figure it out over time. So do we have any other questions? And I need to open a soda or I'm going to cough, so I'm sorry for the noise. So if there are no more questions, I would like to thank all 43 of you who are here for being here. Fenric is making the comment, nah, the expansion rate must have changed with time. Yes, we know it did. but it's not changing the way it is supposed to. We would expect a nice gradual curve that leads to a predictable rate in the past, a predictable rate in the future. And there's the disturbing possibility that the accelerating rate of expansion has itself an acceleration. And then it's turtles all the way down. Now, science doesn't preclude that from being the answer, but the fact that we don't know if it's a science requirement, if we have some of our observations misinterpreted, if we just have the first rung on the ladder of cosmic distance scales not quite right, we don't know what the answer is. And hopefully we'll figure this out sooner than later. And DPI 209, you need to explain to me on Discord how turtles remind you of pizza. That's true, Peter. You can't predict the unpredictable. I prefer not to use the Spanish Inquisition. I prefer to use dark energy as my example. No, Hanny, the answer does not require new particles. This is one of the awesome things, other than figuring out exactly what dark matter is. Our standard model of particle physics also seems to be completely happy. Okay, fine. So Teenage Mutant Ninja Turtles. I'm sorry, I love my actual turtles. Yes, it's true. They were powered by pizza. Don't watch the recent movie. If you like the cartoons, you will hate yourself. Pardon the random editorial. And astronomers are powered by coffee, Larry. So before we go down the turtle rabbit hole, which is, after all, turtles all the way down, I'd like to say once again, the Daily Space is brought to you by CosmoQuest. We are here every Monday through Friday, except for very major holidays. And we are here to bring you science. So thank you for showing up, and come back tomorrow. If you're new, give us a follow. Follows will help you know when all of our different programming comes to a start. Today we only have this one show going on, but throughout the week we have many different programs. This Thursday, in addition to the Daily Space, we're also going to have an episode of Learning Space. Our guest will be David Joseph Wesley, who is a composer who's worked on music you just might have heard and not known was him, that was in the back of, well, Family Guy, Star Wars, all sorts of other amazing mainstream television and film pieces. Now, in addition to that, he also writes music inspired by astronomy, inspired by space. He's been working with Fraser Cain on a piece to, well, animate a video that describes the end of the Cassini mission. He's written music to accompany an eclipse that brings us the science through his music. He's going to be talking to us about where he gets his inspiration, how he does what he does, and his own personal adventures in science. So stay tuned, find out all that we're doing by following us on Twitch, and get that alert that we're going live by following us here, well, on Twitch. Follow us on Twitter, not Twitch, sorry. Follow us on Twitter to get alerts to everything that is coming, and follow us on Twitch to get that notification when we go live. Yes, I can totally drop me the name in Discord or Slack. Not a problem. So Dave is fabulous, and if, like me, you are a fan of Firefly, he has a new CD of space-themed music that is called Music to Smuggle By. Yeah, so I will see you Thursday for Learning Space, and as always, we are sustained by your subscriptions. Every bit helps. And now I am off to do science, and I hope you will do the same over at CosmoQuest.org. And wherever you are in the world, have a fabulous morning, evening, or afternoon. And remember to go outside, and look up. Bye-bye.